Hello and welcome again now to session 6. We're here and you've made it quite far on your journey. We're guiding you through to the digital transformation. We have an amazing session right now. That's one that I'm looking forward to. I mentioned in the morning, this is session 6, solving industrial applications using artificial intelligence. What I really like about this is, again, the use of a new technology in combination with our solutions to really create great benefit at the customer side. You don't have to believe us. We have a specialist here, Christoph Eichhorn, and on top of that, we have somebody from Velux with us, Lasse Heatherby, who will be joining, and I'll let them take it away. The example kind of speaks for itself. Take the floor.
Yeah, welcome everybody, and thank you, Patrick, for the nice introduction. So in this session, we are going to talk about artificial intelligence and specifically deep learning, which is the most prominent technology in artificial intelligence. And as you might have noticed from the agenda, this session is going to be combined with the following session about the app space ecosystem. And we are not only going to connect content-wise between the two sessions, but we're also very happy to have Lasse Heatherby with us today, who is going to enrich both sessions with some exciting application examples from Velux. Before we kick off this session, we would like to show a short teaser in order for the kickoff. Maybe you can start it now. Wow, so what does artificial intelligence and what does deep learning mean to us? If you ask me, there are 2 points that I would like to highlight. The first one is that it allows us to solve more complex tasks and applications than we were able to do so far. And the second reason that I would like to highlight on the second point is that it can tremendously simplify the solution development. The reason for this is that with artificial intelligence, with deep learning, we are moving away from solving applications with a very detailed set of rules towards explaining to our sensor how to solve an application on the basis of examples. And how does that look like? So as mentioned, we need some examples to teach and train our sensor. So in the first step, we will start by collecting these training examples in our application. So that could be, for example, a food production where we want to assess different naturally grown products. And so we would collect training data in the first step with our camera in exactly the same setup as we want to automate the decision-making process later on. Once we have collected enough training data, we will sort this data and upload it to DStudio, which is our cloud tool for the training of deep neural networks. And DStudio will not only train the deep neural network, but also evaluate its performance on some evaluation data. And once we are happy with the outcome of this training, we can download this neural network and deploy it to our sensor so it can autonomously take complex decisions in our application. And to demo this to you, we've prepared a small demonstration based on a bool set assembly check. And what we are going to do here is to check for the different number of lines on such a bool. Those of you who are not familiar with bool, this is a game where the different players or teams intend to throw and roll bools in such a way that They get as close as possible to a target ball, which is called the jack. And the bools from the different teams can be distinguished by the number of lines which have been carved into their surface. So as you can see on this picture, we have some bools with one line and some bools which have a double line to distinguish them. And those of you who have already played this game know that sometimes you have to look twice in order to identify to which team a bool belongs. And this makes it a perfect use case to demonstrate the power of deep learning. So let's assume that we are a manufacturer of these bool sets and that we want to make sure that before we deliver such a set to a customer that it contains exactly the right amount of bools. So we want to have 3 balls with a single line marcation, 3 balls with a double line, and of course no bool should be missing. And furthermore, to provide a nice visual experience to the customer, we want to make sure that the 3 bools belonging to each other are aligned in a row in the set, so they should be, as seen on the left picture, in one line. So how would we do that? In the first step, we will start by collecting training data. The easiest way to do this is to use our intelligent inspection sensor app, which can be used directly on our programmable cameras. And here with drag and drop, we would just mark the different areas of interest. In this case, we have 6 boxes where we would like to inspect later on what kind of bool has been placed there, and we will collect training data with that. Once we have the training data, we sort the training data into the different classes that are relevant to us. In this case, we have 3 classes. The first one with single-lined balls, the second with double-lined balls, and the third one with empty slots that we would also like to recognize if they are present. And now we have a demo video where we show how the training progress looks like. Maybe you can start that one. So this is DStudio, our cloud training tool for deep neural networks. And as you can see here, when we launch it, we get a quick overview and then can start the training by creating and defining the data set. So we define a data set and also define the 3 classes that we want to be able to recognize autonomously. In this case, we start with the empty class and upload the training data that we have. And furthermore, we will also upload data for the other 2 classes, which are the single-lined and the double-lined balls. This data set will be split into 2 parts. Most of the data will be used to actually train the neural network, but we'll also keep some images apart to test and challenge the network. During the whole training process, we always want to make sure that the network really understood the task and not just learned some images by heart. So we do this with some evaluation images that we keep aside for that purpose. The second step is the project creation, where we take our data set and combine it with a neural network that we select here. The selection is quite easy. We offer 3 different t-shirt sizes, small, medium, large. The small networks will have the shortest execution time, and the large networks are able to cope with more complex tasks at the cost of a larger execution time. Now that we have defined the project, we can move on with the training and go to the next step, choose our project and hit the Start Training button. And now we will execute the training of the deep neural network on some very powerful servers for you, which are dedicated to the task. So each training has the best performance. And what you can see here are 2 lines which are showing the accuracy. So in this use case, the neural network is getting very quickly a good result for the classification of different bool balls. You see the red line, which shows the result on the training data itself. So this is perfect. And the blue line shows the result on the evaluation data. And the evaluation data is again looked at in more detail on the following evaluation page, where we can see how well the network was able to cope with the task. And if we're satisfied with it, which is the case here, we can continue and move on to the deployment page. And on the deployment page, we will be able to download the neural network and then deploy it to our camera to enable the camera to take autonomous decisions based on the use case we have just taught into the neural network here. We have prepared also another short demo video to show how this looks like in the application then. So if we can please start the next one. Thank you. So this image is familiar to us from the training data collection step. So we again have the 6 boxes in our bool set where we would like to check if the correct ball is placed in the correct spot. And as you can see now, these boxes have been enriched with a deep learning module, which autonomously decides what kind or what type of ball has been placed in each slot of the set. And in addition to this, we also have the possibility to combine these results to an overall result, which means that we can convert quite a complex situation into a clear decision, false or true. False if it doesn't comply to our requirements, true if it does so. So this is a good example how to convert a complex situation into a clear, simple, and reliable decision. Now, if I could go back to the slides. Thank you. Of course, there are plenty of examples like this that we could show here. I've got a slide here with an example from our own production at SIG, where we produce laser scanners, which need some screw threads so we can mount them later on to their destination. And these screw threads are not meant to be missing, because otherwise that would be an issue when we want to mount the device. And checking this with vision is not easy, because we have reflections, because the surface can be variable and things like that. And with deep learning, this is a matter of hours to solve such an application. Another use case that we have at SIG in our production is the detection of solder joints, where we want to make sure that when we connect to circuit boards with each other, that the joint is correct. And as you can see here, these joints can look very differently, even within a class. So we have 3 classes here, the good one and 2 different error types. And even within one of these classes, we see a high variance, which is quite difficult to put into strict rules. But with deep learning, we will get very good results on such a data set. And a third example where we are using this technology is to check if shielding on a circuit board has been correctly applied or not. This is probably also something that you could do with classical machine vision in a short amount of time. But the beauty here is that with deep learning, it's just a no-brainer to solve it. You just collect some training images for the one case and some for the error case, and then you're good to go. So we've got many application fields where this technology can be used. We've covered 2 of them, the inspection and assembly line, and also the electronics industry and the examples we've shown now. But of course, deep learning is also very good when it comes to naturally grown organic products. An example for that could be food or wood. In the wood industry, we might want to check if the orientation of the annual rings of a wooden plank. And furthermore, we see plenty of possible applications and good opportunities in the food and consumer goods industry for this technology. So you've seen that it's very simple to teach and train a deep neural network for a specific task. When it comes to the integration, you often have to do a little more than just teaching some images and recognizing them. So there are further adjustments which are needed. And for this purpose, you can either use our ready-to-use intelligent inspection sensor app, which is available for our programmable cameras. And in this app, you can just drag and drop modules and configure your application so it does what you need, as you have seen in the examples that I've shown before. And in addition to this, with the SIG app space ecosystem, you can also come up with your very own individual sensor app, which can be even further optimized to comply with the specific requirements of your task. And about the SIG app space ecosystem, Timo Mendler is going to explain it in a much more detailed way in the following session. So I would encourage you to stick with us for the next session as well. And with that, I'm very happy to hand over the stage to Lasse Heatherby from Velux, who is going to share some more examples with us about how to use deep learning. So welcome, Lasse. Thank you for joining us today. And yeah, I would like to hand over to you here. Thank you very much.
Thank you, Christoph. Nice to be a part of this and be with you, although it's virtual. I will start sharing my small presentation here from Velux. In Velux, we have beginning to use machine vision more and more in our production for quality inspection. And in the case of deep learning, we saw an opportunity with the product here from SIG to do it as a more do-it-yourself tool. So we strive to test this. The challenge we aim to try and solve in this application is a foam filling in our shutter profile. And for those of you who obviously know what a Velux window is, you can buy accessories like roller shutters. And these roller shutters consist of profiles that are filled with polyethylene foam to conduct noise reduction and insulation. And this foam filling has to be almost perfect in order to accept the correct quality. As you can see, that is the white part on this image here. But foam, I don't know anybody who is the do-it-yourself type knows that it has its own life when it comes to expanding. And the problem, as shown here, is that the foam can be filled partly, it can be badly expanded, and it can also be emptied if the nozzles are getting stick with residues and things like that. That creates a lot of waste, and it creates a lot of attention for the operators to be aware of this to avoid unfilled profiles into the products. So by saying that, we have tried in Velux to solve this with rule-based vision technologies, obviously edge matching, object locator, blob tools, but as the image show here, the blob can vary in shape and size, so it was really difficult to get a satisfactory result as we believe. So we tried to adapt this deep learning tool from SIG. And in a step-by-step, we started by collecting some live data on the production line by setting up a camera, saving images on a FTP server, then created the data set inside DStudio, as Christoph also showed in his video, by defining different classes and uploading the images. Then we selected a project and a network, and we have aimed to go for the small and medium intensity networks to save cycle time. And then we started to do the training on the datasets. After that, we evaluated the trained network and did a deployment of a trial model onto the production line. This was the first network that we tested, and the result of the classification and the prediction was it was okay, but it was not perfect. So we had to do another iteration to try to improve this, and along with support from SIG, we did an evaluation of the image. For instance, this image is really elongated, so the part of the image that really holds the information that is valuable for the deep learning algorithm is small compared to just the black pixels as seen on these small images, right? So the next steps was to try to improve this by splitting the image up into 3 different images. So we had 3 different networks that we tried to predict on, and then we make an overall decision based on these 3 predictions. Also, we did some segmentation inside the image where we used app space and the tools within the app space framework to crop out the background clutter. And then we also collected more images to train on. This gave us a significantly better results in the prediction when we had a better data set, and I think for almost any machine learning case, that data is of course the crucial part to getting a good result. And by that, I can show here that we have these examples on predictions which are both really satisfactory in the terms of prediction accuracy, but also in the cycle time. This is the small network executed on a small Inspector P device. Another use case where we have tried this is a screw detection in our assembly line. Screws are a crucial part for fastening different components in a window, and these screws and also metal brackets are galvanized, meaning like the screw thread example Christoph showed, that they have different glare and different reflections based on production batch and metal raw material parts. And we spent a lot of time trying to solve this with rule-based vision. And by trying to train this on DStudio, we reduced that engineering time with a factor of 5. So 20% less engineering time to get a good result. And this is really also one of the cases where a deep learning or classification model is useful, that a two-class network, pass, fail, okay, not okay, really gives always a prediction. And in this case, it also gave a really good prediction. And that is even though with images of only, 60 images per class. So this is really, really cool for that part. So that was a little bit about how we have tried to use deep learning from SIG in Velux in my department. I hope this was interesting for you.
Definitely, Lasse. Thank you very much. That was really, really nice example that you have shown to us, which illuminates a little more than our explanation how this can be used and what kind of applications can be addressed with this technology. Thank you for joining us, Patrick.
Well, thank you very much, Christoph, and also Lasse. Very good presentation from afar. Thank you very much. I'm going to get right to the chat because we have a couple very good questions there. One is, you're mentioning downloading the neural network on the camera, meaning the deep learning is on the edge and not on the server. And so this is the idea, or the question is, can you download this to multiple systems on the edge, or is this something that's happening in the server?
No, thank you. That's a very good question. So we have the server to train the neural network, but what we eventually offer is the possibility to have the decision-making process on the camera. And of course, if you have several suitable cameras which are looking at a similar use case, you will be able to deploy the same network also to several lines. Yes.
Right. And that's what I think is very fascinating. And Lasse, this is something you're able to do. You probably weren't just doing this on one camera. You can obviously download this on all of your vision systems that you're using.
Yes, yes. And of course, there's a huge benefit of not being relied on network infrastructure and things like that.
Right, right. So it's right in the camera itself. I think that's a beautiful thing. It's like artificial intelligence in your hand, or at least in the vision system. And you showed very well, Lasse, the benefits that you got from this. And I especially also liked how you worked on it with SIG to break it down into pieces and get even more read rate. That goes into the next question, which is how many pictures or a suitable sample size for the training data? You had mentioned 80, 60, or 80, and also the number 300. I'm going to give this one to Christoph. What is a suitable number? Does it depend on the application itself?
Yeah, it's also a very good question, a bit a difficult one to answer precisely because that really depends a lot on your use case. So if you have a use case where the difference between the classes is huge and the variance within a class is not that big, then you will get very good results even if you have only a few, let's say, less than maybe around 100 images per class to train your network, or even less. But if you have a more complex task where there's a lot of variance within one image class, and you have maybe more than two classes, and sometimes the visual aspect gets close to each other, then you're better off if you collect more data. And in general, I would say the more data you can collect for the training, the better it's going to be, and also the more precise the evaluation, which is ongoing during the training, will be, because it will be relying on more evaluation data as well.
Okay, thank you. We have another good one. I'll give this one to Lasse. This is a question from the chat. When you broke it up into 3 pieces, this problem, Did you need 3 cameras when you needed to split it up into 3, or did you use 3 neural networks that were working on the same camera?
I was using 3 neural networks on the camera, so I was using the one image from the camera and crop it into 3 different images that I was both using for training and also for prediction afterwards.
So we weren't able to sell you 3 cameras. That's okay. No, it's very efficient, and this keeps people coming back for more. So this, I think, answers that question as well. What else do we have? I think that is it. We did get a few questions on this. It was very, very interesting to see. I think it's fantastic. It's available today.
It's available. Please visit us at sig.com/AI to learn more, or go directly to dstudio at dstudio.cloud.sig.com to try it out for your own. And if you have an Inspector P camera, for example, you're also free to download the Intelligent Inspection app from our app pool and get started with this. So please feel free to go ahead and try it out.
Just do it, yeah. Thank you very much. And that ends our session number 6. We're going to be going into session number 7, where we're going to be talking about sensor apps. We've teased it a little bit. Please stay around for this second one. This goes into customizing apps for sensors. It's it's late in the day. I could barely speak, but this goes into our ecosystem at SIG, where we put the power of these apps in your hand. We're going to get into that in just a few minutes. Please stay with us. Thank you.